Welcome to the discussion about bringing streaming technology to a batch world here at Reactive Summit. I'm going to talk a bit about my experience at T-Mobile, where we moved from a periodic chunk-based batch processing system to a fully streaming real-time platform. So, first, I guess I should introduce myself. I'm Jeffrey Sewel. I'm a principal architect at T-Mobile USA. I've been working in the mobile industry for about 15 years now, mostly in the world of data in mobile. And I've noticed every year there's more and more data, more and more effort to keep ahead of it, and it's a problem I think we're going to have to keep solving for many years to come. So a quick overview of our landscape. What is our data that I'm talking about? It's data mostly used to improve call quality of our customers. What I mean by that is it's metadata about sessions that you'll have when you're attached to a wireless tower, where there clicks and pops on the call, where was your browsing experience fast or slow, were there DNS issues along the network. It's not, and this is an important distinction, it's not the data that you would send to your billing. It's not part of your plan information, your billing information. It's all very much the metadata about your technical experience on the network. So how much data am I talking about? Well, there's multiple sources. The final numbers are somewhere in the neighborhood of 600 terabytes a day, uncompressed. And that turns out to be roughly 500 billion, 500 billion records. It's important to note that these records are there's not that many events, it's that we get multiple records about each event. And that data shows up in our feeds, and our customers have use for it. In terms of speed, well, this kind of goes up and down, but we roughly calculate somewhere in the neighborhood of 10 million records every second of one kind or another. Plus or minus 50%, sort of depending on the time of day and whether people are asleep or using their cell phones. And then the question, and I skipped over that a little too much, but the question that I have to answer is how long until the data is useful? So we get all this data, all these records, they come in, millions and millions every second. But one of the problems we have, and I think many people who are looking at streaming technologies will also have, is that wait time until it's useful. And this is useful to our end customers, our business customers internally. And yeah, that number is hours to days before we can actually do anything about the data. So the situation at T-Mobile, starting back in 2016, was we had basic batch processing going reasonably well. This was a large Hadoop cluster on-prem. Data was coming in about once every day. You were 24 to 48 hours from an event before you could actually do something about that data. By last year, 2017, we had started some micro batches. And this would be somewhere in the neighborhood of 20 minutes to an hour, and even a day still for some of the data, before you had full useful data for the customers, our business customers, to use. And then in 2018, our main goal for the streaming platform anyway has been to give us under 1 second. As others have said in the conference today, defining streaming and true streaming is kind of a fuzzy market-ish thing, depending on who you talk to. So we defined it for ourselves. And for ourselves, it was to have data that comes in under 1 second from the file that we source from till it's business usable. So that's the goal for the year. So let's talk about the problem. The first is always a legacy process, right? We have all this data being bundled up, massive amounts of data. The insights are coming later and later. The fallout from that is that our internal business customers weren't able to get any insights until it was too late. Again, it's important to have a distinction. If you're looking at cell towers and say a hurricane goes through, well, we have trucks that roll and people who get out in the middle of the night to go put the towers back up and make sure that service is established so people can make emergency calls. I'm not talking about that kind of response. The basic things, the sort of heartbeat things, are already covered by other teams. What I'm talking about is specifically the business insights. And this goes back to, do you have a good call quality? Did you have a good browsing experience? Little things that over time can add up to a good or bad experience as a T-Mobile customer. But because of the way the data was coming in batch and slow and behind, customers weren't seeing improved service in time for it to matter. Eventually, they just get frustrated, fed up, and move to Verizon or some nonsense. And for the most part, business had accepted that that was just the way it is. The platforms we had, the systems we had, simply could not do better. And that's where I came in and looked at the situation and said, I think we could do better. Ultimately, I disagreed that we had maxed out our capacity. As always, everything we do internally to T-Mobile has to go back to our customer experience. Can we make the customer experience a better one than it was before? And in my view, the goal was to try and find faster response times to these non-critical issues. But if you're having an internet slowdown, if you're having poor call quality, could we speed up the response times to make that better? Second, I was looking for a way that we could reuse the hardware that we had at a lower cost. T-Mobile's invested heavily in data centers and hardware. We're a hardware networking company in a lot of ways. It was very easy to just put a new rack of servers up somewhere. Well, but could we get more out of those servers? And I pitched that as a value proposition for this whole project. But then there was another group that's shown up in the last few years, and I think every company has now a data science group of some kind. And T-Mobile's no different. And this group has come to us over the last few years and said, we want to do real-time analytics on this data. We want to train our algorithms offline, but then bring the results of those into the streaming data and get immediate responses. And then finally, one of our key goals in this project was to better serve law enforcement and emergency responders. I'm sure you've seen TV shows where some nerdy guy's in a back room somewhere and the bad guy's escaping and they say, show me his location. They bring it up on the big map and there's a little dot that goes around the city. Yeah, that's cute and technologically feasible, but no one's doing that. The underlying parts of that are not in place for any of the carriers. But there's a value to that, particularly if you get an Amber Alert. Wouldn't it be nice to be able to immediately say, here's where that person is? So this is the collection of goals that I had as a vision for the future. But as I presented this to management, I was told, well, we've thrown all the hardware we have at it. We have a big, massive server farm, thousands of servers, and it's not happening in real time now. It just can't be done. We just can't keep throwing hardware at this. But, Don Quixote that I am, I said, well, maybe you're wrong. Maybe we can tilt at a windmill or two and change the way it is. Effectively, I wanted to ask if we could do better. So I started an investigation. I said, well, let's look at the landscape that we have and look at what we're doing and see if we can't find places where we could nail the culprit. We could find the person who was the entity responsible for this. So I put together a lineup. And the lineup has your basic criminal elements when you're trying to find a slowdown in a system. The CPU. Could it be the CPU? Are they maxed out? Do we have enough CPU horsepower? Could it be the memory? Everyone loves the memory. It gets cheaper every year, but it always goes over. We always overflow our memory. Could it be this new thing called the cluster? So I think most people here understand that in the last 5 to 10 years, the idea of cluster computing has gone from an academic exercise and a place for specialized labs to the masses, right? From MapReduce to Yarn to now the Kubernetes and the Mesos. We have shifted to the point where cluster is a thing, and it's a thing we all have to work with in some way. And then finally, everyone's favorite villain, the network. Every programmer I've ever known, myself included, says, well, the network's slow. The network's slow. It's just the network. So I set out to figure out which of these might be the culprit. The first place I looked was the CPU. Now, this is an aggregate CPU collection of the entire cluster. So it's a percentage of how much CPU capacity is being used in a given 24-hour period where I took this. And again, it's an aggregate of the entire cluster, so it's not one system here, but this is the combined total. The problem with this was that really none of them ever maxed out. And you look at that spot there, barely 60% CPU for the whole cluster, even during our peak hours. Those spikes you're seeing are the overnight jobs that run that cause a lot of our headache. So now it kind of looks like the CPU might be off the hook. We have enough power, enough capacity. Then I took a slightly closer look at how this went based on the hosts, so individual hosts. And this kind of mess of lines here is one line for each of the different hosts. And you can see that in a few places, they do reach 100% utilization. But why, on the left, is it only at 60? Only certain hosts were maxing out. The others were just fine. They were sitting idle, in fact. So, as much as I liked that bit of data, and much I could see that there was something wrong with the CPUs on individual hosts, overall I had to agree the CPU wasn't the problem. So I moved on to the memory. And this is a chart of the memory utilization, again, by percentage for the entire cluster. And as you can see, we're not getting much over about 70%. 41% is our average. Effectively nothing to see here. The memory looked fine. So let's talk about the cluster a little bit. I had a number of metrics that I could use to decide where the cluster might or might not be slowing down. The one I've chosen here is an indication of how long an application waits before it can start actually running on the cluster. And among the various options we had for the cluster metrics, this one seemed to tell the best story about what was happening. So the spikes that you see there, the ups and downs, those are normal. You would expect when you submit a new job to a cluster, the cluster is going to take some time to figure out where to put all the pieces. The problem you would look for, and we do not see here, was for those spikes to go up and stay up. And actually they don't. They go up and immediately back down. The job's been submitted. Again, there's other metrics we could look at for the cluster, but at the end of the day, this one effectively said the cluster wasn't really waiting for anything. So ultimately, the cluster was fine. So now we're running out of culprits. We go onto the network, and there's a couple things that came up on this. The first and most obvious was that the network capacity was way underutilized. We are, in fact, a networking company. One of the things we do really well is high-speed network backplanes. On the left there, you can see that this is about at 500 meg peaks. These are dual gigabit, 10 gig links. Just from the basic numbers, this is fine. This is way underutilized capacity. And there's no long periods of saturation. The network's just doing its thing. And it's actually on a host-by-host level, pretty empty. So I looked at one more thing with the network to see if I could find a little more under the hood. And that's where I noticed this socket stat receive queue. And this is when data comes in off of the network, before the CPU can pick it up and start doing something with it, it puts it in this little holding area. The kernel puts it in this little holding area. And you can see right here, boy, that's kind of a jump. It's not for an insignificant amount of time. You can't see it too well in this image, but it's about 20 to 30 minutes where the CPU is so busy doing something that it can't service the network data coming in. So that caught my attention. I did have to agree in the end, none of the culprits really stood out as the problem. But we had a few niggling things that bothered me. The CPU wait times, the stats receive time, the wait times for the network data, and certain hosts maxing out CPU while others were sitting idle. As I poked through the various bits of code that were running and looked at these individuals, it occurred to me finally that we weren't looking at an external villain in this story. It was an inside job. That's not something you can say very loudly to your manager. So, yeah, the next thing I did was read out some of this data back to management and said, look, it's an inside job. Our code is the problem. And he said, I can't go to the director with this. I'm not telling anybody that. The fact is, and he wasn't wrong, is that we have a lot of time and investment in the current setup, and that always leads to resistance to changing any of it. And so I had to justify my position. Why was I saying our code was the problem? What kind of a person was I to say something so awful? Well, the fact is the code really was not optimized for these parallel processors. One of the things I didn't show on there was these servers are big and beefy. They have lots of cores. Well, the code didn't know what to do with all that. The same issue with the servers. I mean, if you have a cluster of servers and your job is sitting on one and the other is empty, you need to know how to send the data to the other one to have it process the job. Again, not a thing that had been designed into our code from the beginning. But ultimately, as I researched some more, I realized that the sugar on this particularly bitter pill was that it wasn't really our fault. The developers had done the best they could with what they had and had focused on the solutions they could provide. Fundamentally, the programming stack that we were on wasn't actually designed with parallel processing in mind, and it was showing up in our underutilized resources. So I had to build a proof of concept. I had to show that I wasn't just making these things up, but we could actually make them go faster. And that's what I want to switch to next. So once we've decided, yeah, we think we can prove this, I had to build a proof of concept that shows that new code and a new model, a new stack, could actually fix these slowdowns and get us to true streaming. I also had to forget streaming. In an effort to sell something new to a company like this, I had to simply say, look, this isn't about streaming. Yes, it will be. It's about maximizing our resources. How do we make sure that we're actually getting the best out of the investment we've already put into our hardware? And what that comes down to effectively is non-blocking, multi-threaded, and massively parallel. We needed our code to be able to operate like this rather than to continue operating in a single-threaded world. So I looked around the industry and brought in some hired help. Our in-house experience was mostly SQL and Java. It's where the team had its strengths and had made a good deal of positive impact for T-Mobile. But Scala and the notion of a reactive architecture were very new to us. And so instead of trying to build it from the ground up ourselves and figure out what we were doing, we went ahead and went to the source, and that would be Lightbend. And I think the Bob on the right is my sales guy, on the left is my account manager, but I always get them confused. One of them's the Bob and the other's the other Bob. So we brought in the Lightbend guys to kind of help us understand what massively parallel Scala and Reactive meant and how we could implement it. And everything I'm going to begin discussing in the next part of this really was done in parallel, in tandem with the Lightbend team. We were very appreciative of the work they did. So this first build for a proof of concept, what does that mean? 64 cores. Like I said, we're not short on hardware in our environment. 256 gigs of RAM, 40 terabytes of hard drive, and dual 20 gig links. Yes, they'd upgraded in the meantime. We were not messing around. We were going to show this could work or could not work. So we put together a design, and the design was starting to be something kind of interesting and new. We came up with a pipeline, and in the last 12 months or so since we did this first proof of concept, I've seen this very design start to show up in the industry, and it tells me we're on a right path. So we read a file. Everything we have starts with files. I'll come back to those in a bit. We parse the data from that file. We filter and aggregate those records. And then we cache the data in some place where we can use it and finally present the output. So as a point of reference, I want to show what the existing design looked like. This is, again, very high level. I've washed out a lot of details. I think the important pieces are here. So the existing design, again, lots of different files. Telecommunications companies, in terms of technology, go back quite old, 30 whole years. But the 1980s was actually a very different time for technology. And a lot of the data that we get is sourced from design decisions made in the 1980s. And they just persist. They're not broke, don't fix them. Except that we now have to deal with the fallout. So a lot of very strange data structures. I could spend a whole hour just on those weird structures, but I'll spare you that. Then we moved those files into Storm. And this was the design from 2016 and 17. And the Storm cluster would churn through these files, break them out into records, and put together some enrichment. And so the data would then show up in an HDFS cluster, enriched, ready to be used by the business and actually provide some value. And this works okay. Again, the batch process I was telling you about sits in this space. In 2017, we added HBase to the mix, specifically to start filtering out some data and metadata and then add it to HBase so we could get sort of micro-batch-ish streaming. The daily processes continue on as always, and these are a critical part of our business and have to always be up. The Hive SQL work and the code base we had is still there and will be there for some time. And on the HBase side, we came up with a micro-batch sort of fast data light, the first fast data. It came through an API layer and then on out. Worked in general pretty well. Lots of yarn, lots of intensive SQL rollups going on at the Hive layer. But the delays were still hour and a half to days, depending on the specific report you wanted. So then we sat down with Lightbend and went over what we could do instead. So this is our prototype design. The prototype design started first with, again, the data as a file. This had to always be our starting point. I think one of our goals for next year is to move upstream from that. But for now, files are our source. So this is where we first got into the world of Akka. And this is fairly lightweight in this first prototype. But we used some basic Akka code to pull the data out and then put it into a Mesos cluster that was new for our group. And inside the mesosphere, now we're back in a clustered world, and we used Alpaca. And I'll come back to that, but we love the Alpaca suite. Data gets extracted and put into a Kafka queue. Again, this is the first time Kafka had been at T-Mobile, at least in our side of the house. And kind of opened up a whole new set of possibilities. I just came from a Kafka talk upstairs that was walking through everything that we had done. It was great to hear. Some of these records get queued up in Kafka, and queued's kind of the wrong word. They're hurrying through. Sparks had been on our radar since about 2016 and started to show up a lot in 2017. And this is where we started to do filtering and enriching of the records. And this is, I want to come back to the enrichment piece because it's a fairly important point. But we started some of our early enrichment here in Spark, and then back to Kafka, and then back into Spark for some final aggregations and post-aggregations. And then finally into Cassandra. And Cassandra was a brand new technology at T-Mobile as well. And I want to talk briefly about that because we had a fairly large HBase installation. And one of the design decisions we went through was whether we would stay with that or go to Cassandra. And one of the things that Cassandra had that we didn't see in HBase was the headless architecture. And people who are Cassandra experts can go way into depth beyond what I can on this. But fundamentally, the problem we were trying to solve is parallelism. We were trying to get away from single points of failure, choke point architecture. And ultimately, HBase still has that, whereas Cassandra was able to let us spread out. And yes, the price that you hear when you talk to Cassandra people is eventual consistency, which was a fun thing to learn about. But in our case, it actually, in most streaming cases, I think eventual consistency is fine because you do get the right data. And it's better to get incomplete early data than no data at all. And that's what we were getting with the HBase solution. So Cassandra has been an interesting learning curve also because there's so much you can't do. It's not great at building aggregations and group bys and things like that. But boy, is it fast. And it is not throttled and choked off the way that some of the other solutions are. And then finally, we have an Akka HTTP solution that we showed on the front end that kind of spun all this data up and presented it through a simple web page. There's not a lot of exciting things I can show you, but I can show a little bit about how it went. So when we first presented this is a HTOP, if any of you recognize it. One of the servers in our prototype, each of those lines represents one of the 64 cores in the CPU. We had an hour's worth of data prepared on these servers, and we ran through the demo. And if you blinked right there, you might have missed that. So we were able to push through an hour's worth of data in about 3 seconds. One of the great things about this demo, this proof of concept, was everything ran in parallel. Our CPUs redlined at 85 to 100% across all cores. And the fact is, we couldn't actually bring in files fast enough to feed it. So it was a great first demo. But my bosses are not easily pleased. They said, great, you have a case. You did these things called CDRs. So let me talk briefly about these file types that I mentioned earlier. Without going into too much detail, CDRs are a fairly complex structured file type. Each vendor who produces wireless towers has a controller. This controller produces this CDR file. It's a weird, archaic, proprietary binary encoded formatted thing. It tracks and measures the voice call quality when you're making actual phone calls. Well, it's good and important data set for us, and a lot of revenue is sourced from that. But it's also not the largest data set that we have. The largest data set we have are these things called EDRs, Enhanced Data Records. These are metadata about your web traffic, the browsing that people do. And I think as everyone's noticed a trend in the last 10 years, voice calls are going down, SMSs are going up. As a society, we've just decided it's a little easier to be asynchronous in our communication with one another. And the EDRs that we have actually represent the largest data set that we have. And so I was told, we don't want the little people. We don't want the little guys. We need to go after the Godfather. So let's talk quickly about EDRs. I thought I was done at the CDRs, but no, we have more work to do. Files per second, roughly 200 files come in that are EDRs. This is the bulk of our records per second. It's anywhere between 2 and 12 million. I think that number grows up every day. We had to then enrich the data, and this was something we had not done much of with the CDRs. I want to come back to. And then we have to build some sums and aggregations and finally show and present it. So before I talk about this final step and how we put together the EDR design and the final design that we're launching with, I wanted to pause to consider a few things that also matter. As a group, the team at T-Mobile where we work has a legacy and history of putting together vendor solutions. Big pieces of hardware that move really fast and give great call quality. We were now shifting from that to a software development team. It was no longer enough just to be calling a vendor and beating them up, although Lightbend may disagree with me on that last point. But it was eventually that we had to do the work ourselves. We needed to build a software development lifecycle from the ground up. It really didn't exist before a year and a half ago. And one of the key components of that was test-driven development. And we've gotten a lot of pushback from management on this, but I've consistently stood my ground, that when you have this much data and you're doing this much with it, you need to know that when the developers are done, their code is right. So all of our developers, especially in the first few passes, were given tests. You had to have these tests. Some of them wrote them themselves, but they were given criteria so that they would develop against those tests. And all of our from the ground up, our software has been test-driven development. The second piece of that is integration tests. Again, I think if you go down the path of streaming, I can't caution you enough, these tests matter. Things that you can kind of slide by on an older system or a batch system, you cannot slide by. The first set of code that we deployed to the to the production cluster failed immediately because the integration tests hadn't been done right. So again, those integration tests are just so vital. And then there's other pieces about that deployment, specifically the deployment path. I'm going to go into some of our other pieces in a minute. But when you have code that developers are done with, they need to be done and be able to encapsulate their done and walk away. And then that code needs to be able to automatically go out into production and just work. And that's a lot of effort and work on our side, on the development side, to make right. When it comes right down to it, you're making a Ferrari, and you just can't cut corners on that. So that's my little pause and PSA on, really, you think you have a software development lifecycle, go over it again, because there's probably things you're missing. And we had to build it from the ground up, which was a tedious but also exciting process, and I'm actually quite happy with where our SDLC is these days. So let's talk about the final design. This is the design to give us the EDRs and the design we're going live with production. You can see we've moved the mesos out a bit. It's no longer just, so we had sort of an awkward, abrupt break into the mesos world. We decided to move that out. Super happy, and I'll say this again with the Alpaca group. Those guys were very responsive to some of our early requests, and we're already helping with their pre-release to kind of test it in our staging environment. With so much weird data, with so many weird files, we needed a lot of support and help on this ingestion piece. And I did not get the memo that there was a new Alpaca logo, so this came out first. I like the little picture, it works for me. Anyway, the other piece that we're adding to the mix are Docker and Kubernetes. And the decision around those two really had less to do with performance and technology. It had to do with the previous slide about getting the SDLC, the software development lifecycle, correct. That it's, when you're trying to develop against data that's moving in a streamed pipeline, the developers need sample data to come in and sample data to go out, and they need an actual Kafka to work against on their local system. So that's where the Docker came in and made it much easier for developers to work on their local systems. And we're not as good at that as what we would like to be. With some of the key pieces, we have Docker images that developers can use. And then Kubernetes became kind of a natural fit. It's really hit its stride in the last 6 to 8 months, in my opinion. And it's a great way, if you're following good functional programming rules and staying with your reactive manifesto, Kubernetes is a great way to scale out. And I don't want to get involved in the Akka cluster Kubernetes fight from earlier today, although it seemed the most gentle fight I've ever encountered. Because the Kubernetes works really well for us. You can say, here's my CPU, here's my code. This code never needs to talk to that code. They're both working in parallel and in tandem. So Kubernetes has proven to be a great way to deploy all of these Docker images out and keep them managed inside the umbrella of the mesosphere. One of the other things we did at the entry point, and this was brand new for our group and a huge, huge win. I won't deep dive too much, but there's within the world of Scala a thing called refined data types. And these allowed us, at the point of entry, to, and I went the wrong way. At the point of entry, it allowed us to do data checks. And what do I mean by that? I mean that at the point of entry, we could validate each and every field that comes in, each and every data record, every column of every data record gets a validation at the start. And this was a new initiative started by our director a few months ago, where he wanted us to be able to audit data quality end to end. We have a lot of customers who might come to us and say, well, we ran this query against your data, and I don't think it's right. Well, we needed to prove that it was, or that their query was the problem, but that's never the problem. It's always the data. But we had to be able to show and audit this. And so one of the things we worked out with Lightbend was this refined data types that it's compiled in and it works at speed. None of our speed suffered. We're actually able to start from the get-go with verified quality data. And this has proven a huge, huge win for the team. So then the Kafka, I kind of simplified the Kafka role. Things go back and forth. But then we go into this piece called the enrichment. And I said I wanted to talk about this for a bit, because if, for example, you have a data record that comes in and it has a number in it, and that number maps to a cell tower, well, that number is kind of meaningless to business. It's just a number. What you need is all the rest of the information about that cell tower. And not just the tower, but the antenna. You need to know, what is the tilt? What's the azimuth? How high up is it? What's the latitude, longitude? We have some towers that are mobile. You can actually move them around for special events. Was it in market A or in market B when this data traffic occurred? So from our perspective, to make the data, the raw, high throughput data valuable, we needed reference data. And we're still working through our solution with that, but we're using a thing called Hazelcast. The main goal, though, and the reactive part of this was in that enrichment piece. It's using Akka streams. Is we are able, with about 1 to 2 milliseconds delay, do these fast lookups, send the data down the pipe. And it's these lookups and this reference data that really drives a lot of the business value of the data that we serve. So then the data goes into Spark, and this is where we're getting a lot of interest and attention. So when it goes back into Spark, or in for once, we kind of took out that double loop. This is where our data scientists are very excited. They're knocking on my door every day. Are we ready yet? Can we start putting our algorithms there yet? They've got a bunch of algorithms they want to run. They want to run things on the data as it moves. Well, this is where that's going to happen. Spark is a great choice for that. It has a lot of the built-in foundation pieces that we need for machine learning and those kind of advanced analytics. And one of the upsides of this is in the next stage, where now our Spark jobs can write the old data out. So what you see here at Spark is a split. North, we're actually recreating the existing batch processes, only we're doing it in Spark streaming. And then at periodic intervals, that data is being written out so that customers who are using the legacy data actually have access to that data minutes, not days or hours. By minutes, I mean, I think 15 is our current cutoff. We let 15 minutes go by, then we send it on. Though there was some other streaming before, that's in the southern part of this image. This new data is a substantial increase over the delay before customers could get a hold of their legacy data. And then yes, we have the new data, the faster data. So this is where Cassandra came back and it serves up the Akka HTTP. And yeah, we have a lot of things Cassandra, when you come from a data world, you go, wait, Cassandra can't do group by? It can't do these simple things? It can't, and that's all right because it's so much faster. And we've moved a lot of that over into the far right there, the Docker, the Akka HTTP, where we've done some of the final tuning of the post aggregations. Most of the work happens in Spark. And then, yeah, ultimately the goal of this whole thing was to serve up data as a service. So I don't have any nifty graphics for the final test, but we were able to show EDRs as they happen. We saw roughly a 10 times increase from 200,000 records per second per server to 2 million records per server per second. We'll get through all that. It held parity with what we had seen with CDRs. It included the enrichment. And suddenly, we're able to collapse our servers 5 to 1 from what they had previously been. And as I say there, we have roughly less than 500 milliseconds time from when the data arrives in a file and we see it until it's available on the HTTP side. So the numbers held up, the parallel processing held up. Finally, we're able to give a readout. So we streamed some data and got the buy-in. So we're in the process of rolling out market level streams to each of our markets. So they will have a live feed showing how their towers are doing in real time. As soon as we showed that internally, I had customers lining up, suddenly saying, well, what about this? What about this? What about this? And we have a list of new projects that'll take us well into 2020, to be honest. And I would love to tell you about those projects, but I've been told I can't. But I think if you understand streaming data and the nature of this data, you can probably piece together some of those projects. So there's some takeaways I'd like to go over. At the end of the day, and I formatted this on purpose, that you're a detective. If you're going to build a streaming platform and move away from a batch world, you do have to do your homework and investigation. For all the reasons I said at the beginning, people have an investment in the current way, and you have to kind of gently show them that there's something better. But you have to do it with hard data and with legwork. And ultimately, when you achieve streaming, to get to that goal, you have to achieve efficiency. And that efficiency benefits everybody. Like I said, we're looking at a 5 to 1 drop in the servers for the next few years from what was originally planned. And we aren't largely in the cloud for our group, but that's coming. And one of the things we discussed was that, well, now you don't have cloud processes that are sitting there being blocked that you're paying for. And I said it before, and I'll say it again, build your software development lifecycle. This has to be such an important priority for any of these things to be successful. And finally, what I noticed, that the use cases are there. You have customers who actually want this, but they've written it off. They say, it can't happen, you can't do it. The minute you show them you can, they're very, very excited about it. So that's all I've got. I appreciate your time, and any questions, or we can call it. Thank you.
Questions? No? Oh, there we go. Excuse me.
Thank you for such a nice presentation.
Thank you.
Would you please tell me a few more insights into cluster metrics you looked into? You touched upon it, but I would like to know.
Yeah, that one was a particularly tricky bit of research. So we had to first kind of eliminate that there was just a generic CPU or memory or network problem, right? Because the cluster sits on top of all that, right? So as the cluster sat on top of all that, first I had to eliminate that those individual pieces weren't the problem. So when I say the cluster there, I mean that we were looking specifically at, is the cluster management one of the problems? And I kind of let it off the hook on this, but there are some issues with Yarn, Yarn in particular. And we found that Yarn in our environment was working as well as it could. But so the steps, right, for a cluster is you first submit the job, and then the job, in Yarn's case, has to go out and say, okay, you're going to get this, you're going to get this, and negotiate the resources. And so we had some metrics that would tell us, is it having trouble getting those resources allocated? And the answer was no, it was actually doing fine. The wait times are still an issue, and often when the resources are being requested, we would see backlogs, times when there was a gap from when the resource was being reserved until it was actually being used. And that ended up being kind of one of the things that we puzzled over. Yeah, we worked with a couple different groups on yarn specifically. Ultimately, we figured that our decision was we were doing the best we could with yarn. I'm not entirely convinced it was off the hook in this, but some of the key metrics were okay. I mean, that is, yarn, while it was holding on to resources, it wasn't having trouble utilizing them. When it did run, it ran quite well. The network wasn't a congestion point sending the results set back across the cluster. So those are the kinds of things we had to look at with yarn. There's the whole scheduler piece, which is kind of a key part, more of what I showed here. But then there's the resource allocation phases. And I'm not going to pretend that our Spark on yarn stuff today is 100% perfect. There's still some work we could do there. But for the slowdowns that we were seeing, we couldn't find that the cluster was the cause of them. It might have been a contributing factor, I think, more than I showed, but it was not a cause. So I could probably go into more deep dives to some other charts I have if you want to talk offline. Down here?
2 quick questions. Why are you using Spark on Yarn as opposed to Spark on Mesos? And then for your Kafka consumer, are you using the Alpaca Kafka connector, or what are you using?
Yeah, and I realized after I said that it was a little confusing. The legacy system uses Yarn, and the new system uses Mesos. So the investigation started on the legacy Yarn side. And when we moved it over to Mesos, we didn't have any issues there. So, sorry, that was a little confusing on my part. Yes, we're using the Alpaca Kafka connector. We're using the groups as our way to track the offsets. And yeah, that's been one of the fastest, smoothest pieces in the entire new build. In fact, we've pestered them, like I think I said, to get their release candidate to fix one particular timeout issue that we're seeing that they think is kind of a one-off. But yeah, super fast, really happy with the Alpaca Kafka connector. It's one of the best parts of this whole new build.
So you talked about bringing in Lightbend to kind of help you guys do this stuff. I was just curious about what that process was like and how your developers actually transitioned to designing and developing this way.
Yeah, that was an important part of the entire rollout. Lightbend originally reached out to me. They found me on a LinkedIn. I put some Scala that I've been doing there. And they were like, well, hey, you're doing this. What are you doing? Can we help you? It was serendipitous because at the same time I was trying to look around to see who could help us with this Scala problem. Yeah, so we met with them a few times and went over the proof of concept. The Lightbend guys still kind of remember those calls where they were surprised at how much hardware we were throwing at a proof of concept. So yeah, we had some interactions with them back and forth, and they actually embedded an engineer with us for several weeks, 2 different times, to help me actually build and deploy the first version of this. Yeah, it was a good relationship overall. But then the second part of your question about how we rolled the developers onto it, that's still an ongoing thing. We've had a couple of training sessions now with Scala and Akka with the development team. And one of the things we worked out with Lightbend was to bring one of their people in for a few months. And a lot of what we worked with him on was building this SDLC, because it was so critical to get developers comfortable with moving away from SQL and Java and then moving into TDD. Test-driven development was so important for getting this right. And so there was months of training. We had to build a whole new Scrum, and several headcounts needed to be brought over from other groups to kind of help manage all of this. But yeah, overall, the Lightbend experience, I mean, the sales guy aside, the Lightbend experience has been pretty good. And yeah, we've relied on them pretty heavily for a lot of the onboarding, the training, and the sort of general uplift of the development staff. And forcing a lot of these issues really, really matters. Forcing the SDLC to be correct has really been an important component to all this build out, yeah.
Any more?
Is that bon?
Oh, okay. It's always the other side.
We're doing fine. I know it's the end of the day. You guys just want to head out. I got no problem with that.
Thank you. Hello. 2 questions.
Yeah.
First question is, I'm just curious, what was the management's pushback on TDD?
Without getting myself in too much trouble. I think the general problem, I'll kind of keep it a little more general in my response, is that software development was really new to the management group. They had a few one-off developers, but the idea of having a whole team who did that was really kind of new and shocking to the upper level management. And it took a lot of education to kind of help them on board and understand what was going on. The pushback to TDD wasn't directed at TDD. It was directed at get something out the door now. There's a constant time pressure in a place like T-Mobile to get something out. And for me to push back and say, look, we need to get it out, yes, but we need it to be stable. We need it to be right. Eventually I persuaded them, but there was a lot of view that maybe that was a bit frivolous. No one else has done it in the group. Why should you bother? It's like, this is new. This is really new. Please trust me. And to their credit, they did in the end. But yeah, mostly that it was new and it was kind of scary and they wanted to hurry and show me something, now. Calm down, we'll get there. So it worked out well, but yeah, the pushback was mostly because it was unknown.
Cool, thank you. And the second question is, did your developers do any pair programming?
We did not. Well, I guess a little at the first. No, at the beginning we did. Personally, I have some vacillating feelings on paired programming. I see the value, but it's also like a mirrored hard drive. You've now got one basically wasted resource who only knows what the other resource knows. That's a bigger philosophical discussion. We did it first, though, because at first it really did help to have someone kind of looking over the shoulder of the newer developers and help them understand good Scala methodology. And I do think they all had benefited from that, but it's not a standard thing ongoing, no.
Cool, thank you.
Thanks.
Great talk, thanks.
Thank you.
So, going through this process, how big was the team and how long did it take you to complete those two projects?
The team has grown. It's not nearly big enough. Right now, I think the core development team is 8 plus a QA and a 2 QA and a PM. And then we've had kind of rolling in and out about 5 or 6 more people from time to time for parts of it. The original proof of concept actually was just about a year ago. It was right before Reactive Summit last year. It was the first one that you saw. And then the second one we did in, I want to say March this year. I think it was March. And we kind of started our build out of the production version right around that time. And we're in the final rollout phases now. So it's actually a small team, and our poor Kubernetes guy he needs some help. We love Matt.
Thank you. Great talk, by the way. Can you speak a little bit to the input data sets that you're processing? I noticed on your slide that you have files coming in,
Yeah.
so the frequency of those files coming in, and then looked like you also were receiving streamed messages as well?
We're in early stages of a true streaming right now. There's one source that I can't go into a lot of detail on. Yeah, the files is such an entrenched, established way. My goal for this year was to show that we could do it, and then for next year to get them to then get rid of the files and cut out the middleman. So yes, the target architecture doesn't have files. And we're working on one new proof of concept right now. It's actually beyond proof of concept, showing that we can do an API. In that case, it is an Alpaca API that then syncs to Kafka.
Okay, so you're taking those input files, manufacturing the events, and then processing it from there?
Yeah, extracting the events out of the files, I think but manufacturing, I can see where that would work. But yeah, we're extracting the events out of the files, and that's the event sourcing, and it starts at a file level right now.
Okay, thanks.
Hey, thanks once again. This was a great talk. What was the reasoning behind using Scala if your team was Java proficient and there are Java APIs for Akka?
There were a couple reasons for that. Yes, the why Scala over Java thing, it comes up internally a lot. I may have ruffled a few feathers on making that decision. One of the reasons I decided to do it had to do with a previous project I had done back in 2016, where I had written up a Java module to do a thing, and it was so big, so cumbersome, so ugly, and I had just started to learn Scala on my own. And I said, well, what if I just converted this? What would it look like? So I used that as an exercise to develop a functional Scala version of the same output. The number of lines of code collapsed from somewhere in the neighborhood of 1,500 to about 700. No, 500 by the end. And just to see the code collapse that well, I'm really impatient. I really don't like reading lots of things. So that connected with me. I'm like, that I like. But we had a few people on the team. There were a few Java people who, to this day, still we kind of let them do some Java on the side. We look the other way. A lot of the core team are younger. We had a couple interns get converted to full-time. And then other people on the team, their Java wasn't super leggy. They hadn't been doing it for a long time. And so there was a good team consensus that, yeah, let's just jump in. I mean, I've done Java functional stuff, and it's just really wordy and takes a long time. And also we had the Lightbend people kind of backing the Scala decision. But we had made it before we met with them. And partially it was just I don't like lots of code. And partially it was because I was really drawn to the functional style. And I found it much easier to do functional in Scala rather than Java.
Okay. And just as a follow-up, the result proved to be good Scala code or just really bad Java code in Scala?
I think in my case it was bad Java doing Scala. But it ended up being good Scala code. And actually back to his paired programming question, our early Scala efforts within the team were kind of not great functional, not great Scala. Part of why we brought the Lightbend guys on to help and the paired programming was to fix that. So everyone on the team, we've talked about this internally a number of times, agreed that there was a bit of a bumpy start, but all of them now actually love Scala much more than they did Java. And they're very excited about having switched.
Thanks.
Yeah, and there was one down here.
Thank you. Hello. Do you have any plans to generalize this architecture to other areas like performance management, network performance management, and generalize the virus to the network operating centers?
Plans? Yes. Realistic ones? Yes. You're absolutely right to see that in the design. We saw it too. That there's a good design here, and we worked really hard to make it that way, and it can actually be generalized. So in terms of internal team, we have to kind of build up a little bit before we're ready to take that on, but I absolutely do want to do that. I think there's a great opportunity to roll this out broadly within T-Mobile, and even more generally past that. So yeah, we're working on a few plans and projects for that, 2019 if I'm lucky, but yes, that's very much where I see this going. Thank you.